The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content. You can earn continuing education credits through ACI's online CEU program. Visit www.concrete.org to register. ACI conventions provide an opportunity for networking and for keeping up to date with the latest in concrete technology and practices.
Next speaker is going to be Mr. Fred Goodwin from BASF. He's a fellow scientist there at BASF, and he's going to be speaking on early age repair material properties.
Hello, and thank you for having me. The talk's really in two parts: early age repairs and early age repair material properties. So I've got Janice here looking into the future and in the back. I'm first going to talk about repairs performed at early ages because this is very, very significant. So what is concrete? It's a really cool material. It's economical, long life, low maintenance, doesn't rot, cast it in the field, doesn't burn, bugs and critters don't eat it. We use about 12 billion cubic meters per year globally. That's a lot of stuff. In the U.S., about 1 cubic yard per person per year. Since 1930, over 70 billion cubic meters have been used in the U.S., and we currently have about 10 billion cubic meters that are more than 20 years old. So, looking back in history, we started out with the wood age. We got better building techniques. Then we moved into the Stone Age. Then we made synthetic stone and called it masonry. Then the Steel Age. Well, folks, today we're in the concrete age. Our tallest buildings, our largest structures, our longest dams are all made out of concrete. It's not going to go away. But it's not perfect. Some estimates put the cost of concrete repair protection $18 to $21 billion a year in 2004. Just the cost of corrosion of concrete reinforcement, $125 billion per year. Those figures don't add up. Nobody really knows. Just a couple of weeks ago, American Society of Civil Engineers came up with a new report card. They say we need $3.6 trillion to return our infrastructure to the quality it was in 1988. That's over the next 7 years. That's a lot of money. So, being in concrete repair business is a pretty good business model. It's going to have a lot of work. Why does concrete fail? I say it fails due to the 3 Ds. It starts out with design and construction errors. This is a very famous example, the Leaning Tower of Pisa. If they paid attention to how the foundation was built, we wouldn't have this famous landmark. Those get magnified through deterioration. That's Mother Nature just doing wear and tear on things. And then damage. Incidents like trying to put a 24-foot backhoe under a 16-foot bridge. So, concrete has some Achilles heels. It's not a perfect material. It's relatively low tensile strength. It's about 10% of its compressive strength unless you do some funny things like put fibers in it. Low ductility, it's brittle. It's really heavy for as strong as it is. It changes with time, responds to its environment. Has permeability. It's a hard, wet sponge. And it doesn't like certain chemicals, especially acids. And it cracks. That's the most common failure mechanism for concrete, it's cracking. Furthermore, steel corrodes. Anytime you put steel in a concrete structure, you're basically installing a time bomb. Sooner or later, that steel is going to corrode. That's just thermodynamics. It may be 100 years from now, it's going to rust. When it rusts, it expands, and all of these properties change as the concrete ages. A little more detail. We've got freeze-thaw damage, salt crystallization damage, shrinkage and cracking, thermal movement, fire damage, abrasion, erosion, cavitation, alkali aggregate reaction, sulfate attack, seawater attack, biological attack, excessive loads, vibration and seismic incidents, impact, erosion, reinforcing steel, 3 primary mechanisms: carbonation-induced corrosion, chloride-induced corrosion, and stray currents, or polarization changes in the steel. All 3 of these work together synergistically as well to make the steel rust. So what do we do in new construction? This comes from a website I really like. It's called despair.com. They take all of these motivational posters and they change the captions. Mediocrity. It takes a lot less time and most people won't notice the difference until it's too late. Right back there with those design and construction errors. What's that mean? Usually you inherit the problem, but pay attention to the design. If you only got decent cover over the reinforcing steel, you solve so many problems. Bear in mind that reinforcing steel doesn't stay where you think it is when you place the concrete. Use a low water to cementitious material ratio. And use admixtures as appropriate. They allow you to tune the mixture to do wonderful things. Have the proper consistency for what you're trying to place the concrete at, and make sure it's well consolidated. Above all, properly cure the darn concrete. Keep the water in it until the cement can hydrate. In other words, read ACI. We've got all of this documented. We collect our collective wisdom and publish it in documents. Bottom line, the devil is in the details. Now, Tudi is a Swedish professor, pretty well known about corrosion and so forth. What he says, initially, if I catch corrosion in concrete reinforcing steel, initially I have a low cost. The longer I wait, the shorter the time that the structure lasts and the higher the cost. And doing nothing is the highest cost you can have. So what's that mean? Do unto your future before your future does unto you. Another guy I really like is De Sitter. I think he's from Denmark. He has something called the Law of Fives. He found that if you spend $1 installing monitoring in a structure so you know what's going on before it's too late, that's the same as spending $5 on preventative maintenance before corrosion initiates, $25 on repair and maintenance after it's initiated, or $125 after you've got generalized corrosion. That is, rust coming out of the cracks in the concrete. So you can pay me now or pay me later. In concrete repair, in the process, what you see are the effects of design, durability, and deterioration and damage. You better figure out the cause. One of the beauties of the concrete repair industry, you're going to get the chance to do it all over again if you don't. Then you make a decision, do I repair or not? And a lot of that's determined by how well the concrete was maintained. The trick to concrete repair having a long life is never having to do the repair, to keep bad things from happening before it's too late. Unfortunately, all too often we get to the repair, this is our option. Demolition. But if you're going to repair, do a condition survey. Find out how bad the situation is. Analyze the repair. Develop a strategy. Do the repair. And do maintenance on that repair. A little more detail. There's the 3 Ds. as shown by leakage, settlement, wear, spalling, disintegration, cracking, is repair required? Is it a life safety issue? Is it leakage? Is the structure any longer functional? Does it just look plain ugly? The condition survey, you evaluate, quantify, and document what's going on. Your repair analysis considers both what the owner wants, he's the guy that's paying the bill, and what's possible to do as an engineer. The repair strategy, all three of these came down at the same time. What kind of surface preparation do I do? What's my materials options? What's my methods for doing the repair? A couple of comments on that. We got all kinds of placement techniques for surface repair, stabilization, protection, waterproofing, and strengthening. We got all kinds of repair materials. These are the ones listed in ACI 546. Each one is appropriate in some situations, but not in others. I really like this diagram, probably because I drew it. What this says, how big's my repair? That determines not only how I mix it. If I'm just mixing less than 1 unit, fixing a couple of cubic inches, I don't even think about shotcrete or mobile mixers. I'm mixing it in a trowel and pail or a drill and pail. And it's pretty much always a hand application. When I get serious and I start mixing multiple units, cubic feet, I'm going to be doing a drill and pail, or maybe a grout plant, or maybe a mortar mixer. And that further determines what kind of applications I'm doing. I'm no longer just doing hand repairs, I'm doing things like pre-placed aggregate, form and pour, form and pump. With shotcrete, I'm getting really serious about things. Bottom line, selection is a series of compromises. Try to balance all of these factors to make the best decision. It's not easy. We're working on getting there, but trying to think about all that makes my head hurt and where my hair went. So the trick is to design and maintain concrete to prevent having to repair it. Now, what I was actually supposed to be talking about is early age repair material properties. So in existing construction, the real secret to concrete repair is knowing who to blame for your failures. Okay, so I inherit the problem. Address the problems early in the life cycle. Find the root cause of what's going on. You get a chance to do it over. Fix cracks. Little cracks tend to be bigger cracks. Yes, there is autogenous healing that can happen. Don't bet on it. Keep the water where you're going to need it while you're curing the concrete, and after that, keep the water out. If you keep the water out of the concrete after it's cured, so many of your problems go away. No more freeze-thaw deterioration, sulfate attack, alkali aggregate reaction. And know when to give up and walk away. Okay. A little bit about curing. Anybody know what intermediate curing is about? Intermediate curing is I got the concrete placed, the bleed water has disappeared, but it ain't strong enough to finish yet. I get all these plastic shrinkage cracks. So by doing initial curing or intermediate curing before I can finish it, I'm keeping the water there where it belongs. Now I finish the concrete and I perform conventional curing. This doesn't cost a whole lot of money and it solves a lot of your problems at the get-go. When we start out with cement, we got cement grains. It's free-flowing powder. You mix it with water. Now you get kind of a suspension of particles in water as more or less stable mixture. Bleeding is when it ain't so stable. And I can get settlement shrinkage. I place the concrete. The paste moves as air voids collapse, aggregates wet out. I get cracks forming over the rebar. I can get pockets of settlement underneath the rebar that fill up with water. I get all these problems. Plastic shrinkage. So the water sucks into the substrate. I get cracking. So I need a properly damped substrate. If I use a vapor barrier, that can be good or bad depending on what I'm trying to do. If I'm putting a moisture retaining covering or coating over it, that's a good thing. Mother Nature's trying to take the water out of it. So now the cement hydrates a little more. It gets into these fuzzy particles. It consumes some of the water. I get hydrate rims forming. Viscosity of my material starts to thicken. I get shearing action, but it can be replaced by new hydration product. Eventually, though, those hydrates start to interlock. That's when setting begins and finishing occurs. If I disturb it during this phase, I've just broken those hydrates off. They're less likely to reform. I've caused damage. At early ages, when this is going on, I've got a lot of creep. I've got a lot of shrinkage. Those kind of trade off. I've got a lot of porosity. My strength is low. Cement, as it hydrates, is exothermic. That can create thermal stress. As I said, creep and shrinkage kind of trade off with each other. How's concrete dry? Well, first I got the bleed water on the surface. It evaporates. Then the water evaporates from the pores and is refilled from later on in the concrete. And then finally water evaporates and I get drying shrinkage. Hydration continues, porosity decreases, pore water may be consumed or evaporate, curing is required. Drying shrinkage begins, freezing will destroy the concrete unless it's strong enough. Penetration resistance versus time. Here's strength, there's time, different cement mixtures, different water-cement ratios. And porosity. It decreases with time. Curing. If I moist cure the entire time, I get 125% of what I get if I only cure for 7 days. If I only cure for 3 days, I'm down about 25%. And if I air cure the entire time, about 50%. This is right out of 308. Permeability. This shows water permeation with respect to time for different water cement ratios. Look at this guy, high water cement ratio, it's a sponge. With water permeability, a lot of bad things happen. Chloride ingress, freeze-thaw deterioration. Drying shrinkage, it changes with respect to time, it eventually slows down. How thick is it? How much surface area? What's my surface to volume ratio? Shrinkage is faster at earlier ages. Eventually, concrete becomes this hard, wet sponge. What's the degree of my hydration versus internal relative humidity? The water is consumed, continues to use the water as it hydrates. Furthermore, responding to the environment, if I have dry concrete and it gets wet, it swells. And if I go through these cycles, I get reversible shrinkage, but I can also get some expansion. Looking at repair materials, what about polymer-based materials? Haven't said anything about it. I'm a cement head. I wear the funny white coat in the lab and the funny glasses. You all can talk circles around me with polymer material, so I only got one slide on it. Polymers, as they polymerize, I've got shrinkage, but I've also got high creep. And I've got an exotherm. A lot of that seems to happen at about the same time, so it offsets. However, I can also post-cure. That's heated up after it's already hard. It gets stronger. It gets denser. And I get a small volume change that happens then. So, I had 20 minutes to talk about a lot of stuff. I know I went really, really fast. I'll try to answer any questions you have, and I thank you very much.